So we're going to be learning two new theorems today, the mean value theorem and Rolle's theorem. And they're very, very closely tied together. And they're both going to kind of talk about the derivative and that rate of change. So before we do anything, I do want you to kind of plot these points, right? All of these x and y values. So like 0, 1, 2, 5, 4, 8. Go ahead and pause the video and just plot that. And then we'll restart it. One thing that I do want you to make sure about your graph when you're finished, by the way, is that it comes to a nice smooth, horizontal tangent line at the top. A lot of you guys are still kind of doing something like this where it's not quite smooth and you want to try to graph these with the proper shape, right? So it's really showing that smooth concave down all the way through. So that's kind of what we're looking for, not this guy. So anyways, in calculus, we've talked about the derivative a lot so far. And pretty much the most important thing for the derivative is that we recognize that anytime we see derivative, we want to immediately be thinking the word slope. And another word for slope is rate of change. So slope or rate of change. So we see derivative, we're thinking to slope. And when we talk about slope or we talk about this rate of change concept, we actually have two different types of rate of change. We have an average rate of change and an instantaneous rate of change. And so far we haven't really made that distinction. So we're going to kind of talk about that now. An average rate of change is more similar to what we saw in Algebra 1 and Math 1. And so that's going to be the average rate of change of a function is going to be equal to f of b minus f of a divided by b minus a. And in Math 1 or Algebra 1, we called this m equals y2 minus y1 over x2 minus x1. So this is kind of like the calculus way of writing it. Will be using f of b minus f of a. Those are our y values. Over b minus a, those are our x values. And so what the average rate of change represents is it's the slope of a secant line. And so if we're asked to find the average rate of change on the interval from 2 to 12, we can do that with the formula, but just to see what that represents up on the graph is if we plotted the point at x equals 2, right? And at x equals 12, if we plotted those 2 points, and if we created a line through them, right, this would be our secant line. Right, and so our secant line, that's, basically the slope of the secant line is equal to our average rate of change. Okay, now, another important thing is, that anytime we have average rate of change, it's between 2 points. So it's the slope between 2 points. Right, so in this case, we have, when we see the word interval, we know that this is not an x comma y, that those are two x values. Right, and so what we're going to do is we're going to write, kind of the average rate of change will be equal to, in this case, so 2 is our a and 12 is our b. So this will be equal to f of 12 minus f of 2 divided by 12 minus 2. And that's going to give us our f of 12 value, right, was 8, or you could do it on the graph at 8, and f of 2 is 5, or you could do it on the graph, 5. So 8 minus 5 divided by 10, and so we get 3/10. And so that's our average rate of change between 2 and 12 is 3, 10. Right, and we said there were 2 points. You don't have to write this necessarily, but just to kind of think about it with, having 2 points is the points would have been 2, 5 and 12, 8. So we're looking for the slope between those 2 points, right? And this is just, like I said, y2 minus y1. If you jump down here, it's kind of y2 minus y1 over x2 minus x1. So I like to kind of think of it as the calculus way of doing y2 minus y1 over x2 minus x1. Next, we're going to get into our instantaneous rate of change, and this is something that we're a little bit more familiar with, right? The instantaneous rate of change, that's the slope of the tangent line. Right, and so we find the instantaneous rate of change, and instantaneous means at one instant. And so we're going to kind of think of that as being at 1 point, right? So our instantaneous rate of change, that formula is just f prime of a, right? That's our instantaneous rate of change. So instead of being between 2 points, it's the derivative or the slope at one point, at one instant, right? And so this question here asks, is the instantaneous rate of change of f at x equals 4 greater than the instantaneous rate of change at x equals 6? So at x equals 4, right at that point, we would draw a tangent line, right, that hits it in one spot. And this would be the tangent line at x equals 4. And so that's going to represent, the slope of this line will be f prime of 4. Then we could also do it at x equals 6, right? And so here's our tangent line at x equals 6. And this slope is going to represent f prime of 6. So which one of these two slopes is greater will kind of be based on which slope is steeper, right? And so the tangent line at x equals 4 is steeper, so we can say f prime of 4 is greater than f prime of 6 because, essentially the slope, or we could just say the tangent line to f of x, we always want to say like the tangent line to f of x at x equals 4 is steeper than the tangent line to f of x at x equals 6. So that's a perfectly good explanation. There's a second explanation I do want to kind of just touch on that we could use. And so this would have to do with concave up and concave down, right? So what does concave up and concave down represent with the derivative, right? So we said if f is concave down, or up, we'll go with up first, f double prime is positive, but the other connection we made is that f prime is increasing. And we saw a couple of these questions on the test, on the quiz for the last unit, where it might be what's a possible value if f is concave up or if f double prime is greater than 0. And, so that change in the slope is getting bigger and bigger and bigger. And then if f is concave down, then we know that f prime is decreasing. And so this graph, the graph in blue, right, is concave down the whole time. So we know that f prime, the derivative, is decreasing. So that means the derivative is getting smaller and smaller and smaller. So it doesn't matter what the derivative at 4 is, right? We know that if we go left to right, the derivative is decreasing, right? Because our graph is concave down. And so since 6 is bigger than 4, we know that its derivative will have to be smaller. So we can kind of say, another way of saying this could be that f prime of 4 has to be greater than f prime of 6 because f of x is concave down. So f prime of x is decreasing. So if we know it's decreasing, then as we move from left to right, our derivative will get smaller and smaller. So either one of those two explanations would work. Now we're going to move on to Rolle's theorem. You can pause this video and just kind of copy down this theorem and then restart it. Make sure you have this copied down before we talk about it because it is kind of tricky to think about. So if f of x is continuous on a to b and differentiable on a to b, and f of a equals f of b, then there is guaranteed to exist a value c such that a is less than c is less than b, where f prime of c equals 0. These theorems, when you read them, are a lot. So we want to kind of break it down. So whenever we see the word if, that's kind of our conditions. That's showing us our conditions. So the first condition is that f of x is continuous. The second condition is that f of x is differentiable. And you'll notice the difference in the brackets, right? And the reason for the brackets is if we have kind of, some a to b, right? We call it continuous at the endpoints because we plotted a point. So that point exists there. But we don't call it differentiable at the endpoints because we can't draw a tangent line at the endpoints, right? There would be no way to draw a tangent at those endpoints. So we call it kind of a cusp at the endpoints. It's similar to having a cusp or a corner at the endpoints. And then our third condition is that f of a equals f of b. So we wouldn't actually want to use this graph as an example. We would want to use a graph where essentially where at a, our y value, our f of a, is the same as our y value at b. So it could be a parabola, it could be kind of something that squiggles, but essentially we know that those y values are the same, right? So that's that third condition. Then there is guaranteed to exist a value c such that a is less than c is less than b. So that's telling us that c is in between the interval. C is somewhere between a and b, where f prime of c equals 0. That's kind of our result. Okay. So our result is there has to be an f prime of c equal to 0. So somewhere in there, there's a slope of 0. Okay. So if we consider the function presented on the previous page, does Rolle's theorem apply on these intervals? So from 2 to 12, right? So at, essentially from x equals 2 to x equals 12, right? Those points that we'd already drawn in green. So our three conditions are f of x would need to be continuous, it would need to be differentiable, and f of 2 would have to equal f of 5. Well, f of 2 is 5 and f of 12 is 8, so that didn't match. So kind of we could say that, if we were, you don't have to do this, but if we were kind of thinking about the three conditions, right? F is continuous on 2 to 12, right? Every single point existed. F is differentiable on 2 to 12. Remember, the way we're going to figure out if it's differentiable or not from the graph is, and this one uses parentheses like we talked about, the way we're going to figure out differentiability, just kind of as a reminder, from an F graph would be we want no corners and we want no cusps. And then we also want no discontinuities, right? So no jumps, no holes, no vertical asymptotes, none of those little oscillating parts. So we're looking for cusps, corners, or discontinuities. And so those two did work, right? Those two did work. But then f of 2 basically was not equal to f of 12, right? Because we said 2 was not equal to, 5 was not equal to 8. Right, so we could kind of say Rolle's theorem does not apply. Did I mess this up? Yeah, I totally misread that. That's 14. Okay, so this is 2 to 14. 2 to 14. So let's check for 2 to 14. So for 2 to 12, we would say it doesn't apply. But this was actually 2 to 14. So let's go in and fix this. So at 14, this is my fault. 14, here we are. So that point is 5, right? They're the same y value. And if we look here, at 14 we're 5, at 2 we're 5. Okay, so those are equal to each other. So f of 2 equals f of 14. We could say 5 equals 5. So this one we're actually going to, all three rules pass. So we'll say Rolle's theorem does apply. You'd also say is applicable. So does apply on, or let's say 2f. That's a little bit better. 2f of x on 2 to 14. And we need to just kind of explain all three of those because f is continuous on 2 to 14, brackets. F is differentiable on 2 to 14, this one with parentheses. If you mess up the parentheses and the brackets, they're most likely not going to ding you. And f of 2 is equal to, I'll say 5, which is equal to f of 14. If you didn't have the 5 in there, if you just said f of 2 is equal to f of 14, that's fine. And so, we could even go a step further, and we'd say, where does f prime of c equal 0? Right? So in here, is there a value where it equals 0? And yes, at 8, right, if we drew kind of that's where we would draw our f prime of c equal to 0. Right? So our value c in this case would be 8, right? That would be like the x value where we had a slope of 0. Now, it didn't ask us to find it, so we don't have to. But that's kind of, just kind of thinking one step further, right? So now in the second one, right, first of all, f is continuous this whole graph. So we're going to say f is continuous from 2 to 8, and f is differentiable in this whole graph. There are no cusps, no corners. But now when we look at the y values, right, at 8, our y value is up at 11, right? So at 8, our y value is at 11. So f of 2 does not equal to f of 8, right? Because 5 is not equal to 11. Now, when it doesn't apply, you don't need to explain all three rules. Just explain the rule that didn't work. So we'll say Rolle's theorem does not apply to f. Now, it's always important to include the interval that you're talking about because it does apply to f for different intervals, right? But it just doesn't apply from 2 to 8 because f of 2 is not equal to f of 8. And so there's that. So before we move on, I do want to talk about kind of why Rolle's theorem is the way it is. And what I want us to think about is if I knew I had a y value, let's say this, we'll call this a, but we'll call it at 1, right? We knew we had a y value at 1, and then somewhere at b, it was 1 again. Well, if my graphic goes up and it's continuous, then it'll have to come back down, right? And then we can get back there. Now, it could happen more than once, right? Like we could go up and then we could, kind of go up again. We could go down and go up again. And then this time we have, 1, 2, 3, 4 of those horizontal tangents. But essentially, if it's continuous and it's differentiable, then we know that when our graph essentially goes, up, right, it has to smoothly kind of come back down. And the reason it has to be smooth like that is because it's also differentiable, right? And so that creates, at that maximum value, that creates a horizontal tangent, which is where f prime of c equals 0. So that's why Rolle's theorem works. Now, if we weren't differentiable, right, if our graph was not differentiable, then what could have happened is it could have gone up, made a corner or a cusp, and come back down, and never, had a horizontal tangent, never had a slope equal to 0, right? So that's why it has to be differentiable. It has to be continuous because, the other thing, right, it could have gone up, had a hole here, and gone like that. Or we could have had a, vertical asymptote where it went up to infinity and came back down and never had a slope of 0. So that's why it needs to be continuous. But if it is continuous and differentiable, right, when it returns, if we look at this guy over here, right, it comes down and it makes that horizontal tangent. Now it has to make just one. It could make more than one, but it has to make at least one. Okay. And even a straight line, right, if we had a and b, even if we just had, a completely straight line, that has a slope of 0 the whole way. So it has to have some slope of 0. Okay, so now moving on, for each of these, determine whether Rolle's theorem is applicable, and then apply it to actually find out the value. So in this case, one, f is, or we're using g this time. So g is continuous essentially for all real numbers because it's just a polynomial. But we're going to say on -3 to 0, right? So anytime we just have a polynomial, we don't have a fraction, we don't have ln, we don't have any trig, we don't have a radical. It's just continuous everywhere, right? Same thing with differentiable. You could take the derivative, it's 18x minus 4x cubed, and that's also a polynomial. So g is differentiable everywhere, for all real x, but we'll say on -3 to 0. And then our third rule is that g of -3 has to be equal to g of 0. So what I do is I just plug in both of them. So 9 times -3 squared minus -3 to the 4th. Okay, that gives us 9 times 9 minus 3 to the 4th is 81. And that's 81 minus 81, or 0. Right? So then if we do g of 0, we're going to get 9 times 0 squared minus 0 to the 4th equals 0. So we can kind of say, therefore, Rolle's theorem applies. So now that Rolle's theorem applied, now the second part of this, was to then go and actually find the value of C. So what does Rolle's theorem tell us? Rolle's theorem tells us the result is that f prime of C equals 0. So those three rules is just to see, can we use it? Now that we know we can use it, now we can take f prime of C essentially and equal to 0. So first we're going to find f prime of x. Right, the derivative f prime of x is 18x minus 4x cubed. So that's our derivative. Now for f prime of c equal to 0, what we're going to do is we're just going to change our x's over to c's. And we're going to set this equal to 0. So we can factor out a 2c. That gives us 9 minus 2c squared equal to 0. And then from there, we just set each side equal to 0. So we'll set 2c equal to 0. And we'll get c equals 0. And we'll set 9 minus 2c squared equal to 0. That'll give us 9 equals 2c squared. Divide by 2. 9 halves equals c squared. Square root both sides. And we get c equals plus or minus. The square root of 9 is 3, right? Because we can do the square root of the top and the bottom. So I'm going to say 3 over square root of 2. Now, there's one last step, okay? You're going to want to box all three of them, but you can't box all three of them. The last step is that we actually have to go back and see which ones are in between -3 and 0. So 0 is an endpoint. It's not in between. And then here, this is c equals positive 3 over square root of 2. And c equals -3 over square root of 2. Those are decimals. I know we don't necessarily know exactly what decimal they are, but what I do know is that between -3 and 0, everything is negative. So I know that this guy cannot be in between. So we only have one value in this case, and it's -3 over square root of 2. You don't actually need to know what the decimal is because since Rolle's theorem applied, we know we have one value. So we know that that value will be within. But if you really wanted to kind of double check it, you could take out your calculator and just type in control divide -3 over square root of 2. Hit control enter to make sure you get a decimal. We get -2.1, which is in our interval. So we're good. Okay, next we have sine of 2x divided by x plus 2. Now, sine and cosine are continuous for all real values. So the numerator is continuous, but the denominator is not continuous, right, at x equals -2. So basically x equals -2 is, where g of -2 is undefined or DNE. So it's not continuous. X equals -2 is not continuous. Right? If we thought about our three continuity rules, g of -2 just, you can't plug it in. And so what you want to double check is -2 in this interval? Sometimes it's not. If they had said from 0 to 6, then we would have been able to do Rolle's theorem. But in this case, -2 is in between -4 and -1. So we'll say Rolle's theorem does not apply because g of x is not continuous at x equals -2. And if you want to go a step further, you could say, because g of -2 is undefined or is DNE. So there's that one. Moving on, Rolle's theorem guarantees that if a function is continuous on the interval and differentiable on the interval and f of a equals f of b, then there is guaranteed to exist a value of c on a to b where the instantaneous rate of change is equal to 0, right? So the formula is f prime of c equals 0, but I just want to talk about, what is f prime of c? Going back, right? We said that f prime of c is defined essentially as our instantaneous rate of change at c. So somewhere the instantaneous rate of change is 0. Now, mean value theorem is similar, okay? And actually Rolle's theorem is a specific case of the mean value theorem. So Rolle's theorem is kind of part of the mean value theorem. So the mean value theorem is a little bit more general. It's kind of like squares and rectangles, right? All squares are rectangles. So a square is a type of rectangle. And so Rolle's theorem is a type of mean value theorem. And we'll kind of see that. So, pause this video, copy this down, and then we'll talk about it. So if f of x is continuous on a to b, so that's our first if, right? The ifs are our conditions, and differentiable on a to b, starts off the same way, then, so there is no, what they took out is there's no, it's kind of missing the f of a equals f of b, and that's why Rolle's theorem is a special case of it. Rolle's theorem is basically mean value theorem with this extra f of a equals f of b part. So just those two conditions, if it's continuous and if it's differentiable, then there is guaranteed to exist a value c such that a is less than c is less than b. Same thing where we're in the middle, where f prime of c is equal to f of b minus f of a over b minus a. And so I want to talk about that with a graph really quickly, kind of maybe in the bottom we can just draw a graph. And in this case, if we draw a and b, the y values are not equal to each other, right? And so just kind of draw a graph. You can make a parabola or something like that. And so, when we look at this, when we think about f prime of c, that's an instantaneous rate of change. So that's some tangent on the graph. So when we talk about f prime of c, we're talking about some tangent on the graph. When we talk about the f of b minus f of a over b minus a part, when we talk about this part, that's our average rate of change. Remember we said that's our secant line. So that part is the slope of our secant line. So this guy's slope, right? This is the f of b minus f of a over b minus a part, right? So if we kind of used a highlighter, right, that's that part. Then so an f prime of c we said is some instantaneous slope, some tangent line. So is there a spot here where the tangent line, where the slope is equal, right? And if we kind of look and we try to figure that out, right, kind of thinking, okay, this slope, maybe that slope looks like, I don't know exactly where, but it looks like maybe somewhere about there. If I drew my tangent line, those are going to be pretty close, right? I don't think I got it exactly, but those are pretty close to parallel. Maybe it's a little bit earlier to get them perfectly parallel. But, that's our f prime of c. All right, and so those are hopefully parallel when you draw it perfectly. And so what happens is if we kind of look at the tangent lines, see how this tangent line is negative, right? And it's basically too small. And then this tangent line here is too steep. But if we kind of thought we kept changing it, somewhere around here is that perfect part where they're totally parallel. And so that's kind of how mean value theorem works. So if we consider the function h of x equals 3 minus 5 over x, and the graph of h of x is pictured below, does the mean value theorem apply on the interval from -1 to 5? Explain why or why not. So in order for it to apply, all we're thinking about are our two conditions. So our first condition is that h of x must be continuous from -1 to 5. And our second condition is that h of x must be differentiable. And again, as soon as one doesn't work, you don't even have to move on. So for continuous, where is this graph not continuous? Well, we have a denominator, right? And it's a little bit easier if you kind of, go 3x over x minus 5 over x. And get this to 3x minus 5 over x. But we have a denominator, right? So we know we're not continuous whenever the denominator is equal to 0. So basically for this function, x cannot equal 0. And is 0 in between -1 and 5? Well, yes, 0 is, -1 is in between, or 0 is in between -1 and 5. So we would say mean value theorem does not apply because h of x is not continuous at x equals 0. And we should add on does not apply, right, to h of x on the interval from -1 to 5. That part's important because mean value theorem will apply in other places. Does the mean value theorem apply on the interval from 1 to 5? Well, in this case, it does, because our only value that x can't be is x can't be 0, right? So from 1, at 1 we have, y value there, to 5, we can see through that whole section of the graph, it is continuous and it is differentiable, right? And it's basically because the only spot where it's not is at 0. So mean value theorem does apply, again, to h of x on 1 to 5, because h of x is continuous for 1 to 5 and differentiable in between 1 and 5. So graphically, what does the mean value theorem guarantee for the function on the interval from 1 to 5? Draw this on the left. So this is very similar to kind of what we were talking about here. So graphically, we need a value c whose tangent line to h of x, essentially, is parallel or has the same slope to the secant line between x equals 1 and x equals 5. You'd say over the interval from 1 to 5, either way. So then draw this on the left. So we'll draw our secant line. So our secant line is that line, going through 1 and 5, right? And so that's our, f of 5 minus f of 1 over 5 minus 1. That's our secant line. And so we need to find a spot where it's parallel. To me, it looks like it's a little bit after 2, somewhere in there. If we draw that line, those look pretty parallel. And so this is our f prime of c, right? That was just hitting it right, like I said, a little bit after 2. And so now apply the mean value theorem to find that value. So the way we do that is we want f prime of c equal to f of b minus f of a. So first we're going to find f prime of x. And the 3, when we take the derivative of 3, that goes away. The derivative of negative 5 over x, right? So negative 5 over x to the first, I'm going to use that reverse power rule. I'm going to multiply that up, change the sign. Negative 5 will turn to positive 5 over x squared. So that's our f prime of x. And so when we do mean value theorem, we change the x to a c, so 5 over c squared. And we do f of b minus f of a over b minus a. And a big thing that students do here is they plug it into the wrong spot. This says f of 5. A lot of students will then plug it into f prime. It doesn't say f prime, right? It says f of 5. So we're plugging in those to the original value. So we're plugging those in here, 3 minus 5 over 5, right? That's 3 minus 1, which is 2. Or you could have just looked at the y value. At 5, our y value on the graph, because we were given a graph, was 2. So we're going to say 5 over c squared equals 2 minus 3 minus 5 over 1. 3 minus 5 is negative 2. Or again, we could have looked at the y value on our graph. That should have been a 1, not an a. Over 5 minus 1 is 4. So that's 2 plus 2 is 4. 4 over 4 is 1. So I'll write this up here. That gives us 5 over c squared equals 1. Now we can cross multiply, right? Lollipop that, cross multiply. And we get c squared equals 5. Then we're going to take the square root of both sides. And so we get c equals plus or minus square root of 5. Now remember, we said both of those might be correct, or maybe only one of them is correct. So if we think about c equals positive square root of 5 and c equals negative square root of 5, are they both in this interval? Well, positive 5 is in the interval, but negative 5 is not. Right? I don't know what the decimal for square root of 5 is. You don't have to report it because this is not a calculator question. But we do know that, like, basically 1 squared is 1 and 5 squared is 25. So the square root of 5 is in between those because it's in between 1 and 25. So explain why you cannot use our mean value theorem for f of x equals x to the 2/3 minus 2 on the interval from -1 to 1. Well, x equals 2/3 is actually continuous, right? Anything that has a fraction, essentially if the bottom number is even, then your inside x has to be greater than or equal to 0. It's like a square root. But if the bottom is odd, then it's actually continuous for all real numbers. And that's because of how how this works, right? So a cube root, you can cube root any number, but a square root, you can only square root 0 or positive numbers. So in this case, we have a cube root, right? So we know it is continuous for all real numbers. So if we were kind of thinking of our two, in this case, we only have two ifs. We have two conditions. F of x actually is continuous for all real numbers. So it is continuous for -1 to 1. But generally what cube roots have is anytime you have a cube root, right, they either look like, if it's just x, cubed, or cube root of x, either one. What those generally look like is they kind of look like a radical and then another radical, but they're not differentiable at 0 because it makes that vertical tangent line. I think I forgot that up here. If you want to add that to your notes, where we were talking about not differentiable, somewhere up here. No corners, cusps, or I forgot the vertical tangent line. Or no discontinuities. So on cube roots, they make those vertical tangent lines. And if instead they were like x to the 2/3, right, what that does is it squares this side. So then it becomes a cusp, right? It's that side's on the left, and it kind of repeats that on the right. So either way, it's still not differentiable at 0. So these usually have a non-differentiable part wherever this, whatever's being cube rooted is 0. So if you could see that, and you can just jump straight to saying, you're kind of smart about it, and you can just jump straight to saying f of x is not differentiable at x equals 0 because it has a cusp, that's great. But if you want to show your work, I think that's a little bit smarter. So what we could do is we could kind of show it. So we would do f prime of x equals 2/3 x to the -1/3, right, when we subtract, and then the -2 goes away. And so that's 2/3x to the 1/3 power. We want that to be 0 or undefined to get our critical points, but really we're just looking for where is it undefined. So the derivative would be undefined when the denominator is 0, right? So whenever the denominator is 0, that's going to be where the derivative is undefined. And so basically for the derivative, 3x to the 1/3 can't be 0. And so if you divide by 3, cube both sides, we would get x cannot be 0 for the derivative, right? That would make the derivative undefined, right? Critical points are where the derivative is 0 or undefined, and the undefined is the bottom being equal to 0. So in this case, f of x is not differentiable at x equals 0. We kind of showed this, basically because f prime of 0 does not exist or is undefined. And so they want us to explain why Rolle's theorem does not work. So our explanation would essentially be Rolle's theorem does not apply to f of x at or over or for -1 to 1 because f prime of 0 is undefined. Or you could say, because f is not differentiable on -1 to 1. So that's kind of our explanation there. Find the equation of the tangent line to the graph of 2x plus sine x plus 1 on the interval from 0 to pi at the point which is guaranteed by the mean value theorem. So in this case, they're already kind of telling you that the mean value theorem applied. So we don't need to check the continuous and the differentiable. because they're telling us it worked. So what we're going to do first is we're going to take f prime of x, and that's going to be 2 plus cosine of x. Then we're going to change the cosine of x to a cosine of c. We're going to equal that to f of pi minus f of 0 over pi minus 0. Some people like to do this part off on the side. So I'm okay with that. What some people will kind of do is they'll first find f prime of x, and they'll say, okay, so f prime of c equals 2 plus cosine of c. And then what they'll do is they'll say, okay, what's the average rate of change? Right, that like f of pi minus f of 0 over pi minus 0. And they'll do these separately, and that works for them, and that's great. So, and they might even do everything kind of in its own line. So f of pi is 2 pi plus sine of pi plus 1. Sine of pi, right, is 0. So this just gives 2 pi plus 1. And then they would do f of 0, right? That's 2 times 0 plus sine of 0 plus 0. I'm sorry, plus 1. And sine of 0 is also 0. So this is 0 plus 0 plus 1 is just 1. And so then they would say, okay, so our average rate of change is equal to f of pi was 2 pi plus 1. I like to put these in parentheses, minus 1, just to make sure we're plugging in correctly, over pi minus 0. So 2 pi plus 1 minus 1 is just 2 pi over pi. The pi's cancel, and so we just get 2. And so then what they're able to do is they're able to just say, okay, 2 plus cosine of c equals 2, right? They just take that and they put it in. You can do it that way, or if you did it all in one line, you just kind of continued this work down and just kept rewriting 2 plus cosine of c on the left side, you can do that also. So either way works, just make sure you kind of don't get lost. So now we subtract 2 to both sides, we get cosine of c equals to negative 1. To 0, I don't know where I got negative 1, right? 2 minus 2 is 0. And so you take the inverse cosine. If you want to show your work, you would be taking the inverse cosine, right? And your calculators can kind of do that as well. I'll have to show you guys a little bit later, but that's kind of the math part of it. But what we're thinking is, okay, where on our unit circle or where in that chart, does the cosine equal to 0, right? So actually, I think the cosine being 0 is way off on the right. So we're on that chart, and so cosine is 0 at pi over 2 and at 3 pi over 2. Those are the spots where cosine is 0. Now, the issue is here, this graph didn't give us an interval, and that's kind of my fault, is I should have said at the first point, maybe in quadrant 1 or something like that. Or we should have given you an interval. Oh, we did give you, I don't know what I'm doing. Okay, between 0 and pi. I don't know how I missed that. Okay, so between 0 and pi. So 3 pi over 2 is not between 0 and pi, right? 0 to pi is just there. So pi over 2 is our only point. So our c value would be pi over 2, right? Because of that interval. So now they asked us to find the equation of the tangent line that works for that. So our x1 is going to be pi over 2, right? That's the x1 is the value that we found. Okay, our y1, we're going to have to plug in pi over 2. So for our y1, we're going to have to kind of do f of pi over 2, which is going to be 2 times pi over 2 plus sine of pi over 2 plus 1. Here the 2's cancel. Sine of pi over 2 is 1. So we get pi plus 1 is pi plus 2. And for m, you could plug it in, or you could realize, hey, wait, the m is that guy, right? The m is, we had just solved for this. We said that this is where the instantaneous rate of change is equal to the average rate of change. So we know that the m has to be 2. But if you want to plug it in, you absolutely can, right? So f prime of x was 2 plus cosine of x. So f prime of pi over 2 would be 2 plus cosine of pi over 2. So 2 plus cosine of pi over 2 is 0, so we get 2. So that worked. So there's our x1, our y1, and our m. I'm going to just kind of write it above. Y minus, now in parentheses, pi plus 2, right? We need to make sure there's parentheses there because the negative will distribute to both of them. Equals 2 times x minus pi over 2. And that's our tangent. So there's that. That's kind of the end of the notes, but I do want to talk about one thing because I have seen the AP test test mean value theorem without actually using the words mean value theorem. Instead, they use, they ask you to find where is the instantaneous rate of change equal to the average rate of change. And that is what mean value theorem is saying, right? Is they're saying where does f prime of c, the instantaneous rate of change, equal to f of b minus f of a over b minus a. So it is very important that we kind of understand instantaneous rate of change means f prime of c or f prime of x, and average rate of change means f of b minus f of a over b minus a. So if a question doesn't say anything about the mean value theorem, but it says find the point where the instantaneous rate of change is equal to the average rate of change, we're still going to do this same formula.